Good morning. Another day, another chapter. Today we're going to be looking at chapter 29. And chapter 29, the title is a little intimidating, maybe. Chapter 29, Electromagnetic Induction, Faraday's Law. What chapter 29 is actually about is how do we generate electricity? So how do we get electrical currents going? Now, we've already talked about batteries. We run chemical reactions, but now we're going to look at how do generators work? How do we actually spin generators and create electric currents? So I'm suggesting that we use a different title for the chapter. Let's generate electricity. That sounds like a lot more fun than electromagnetic induction and Faraday's law. Because basically that's what we're doing. Now, I tried to think of the simplest approach. What would be the simplest way to demonstrate how electricity gets generated? And here it is. See what you guys think. So here's my light bulb. I want to generate an electric current that runs through this circuit that I have set up. So what I'm going to do is this. Here's my light bulb. I'm going to attach some wires to that. I got some wires attached. They don't connect over here. What they do is the wires run along these lines. And then what I'm going to do is I'm going to take another piece of conducting material and I'm going to run that conducting material along so that it stays in contact with the wires. Now here is a region where there's a magnetic field. And so if I take this conductor and I move it back and forth in this magnetic field, let's see what happens. First of all, let's take that conducting piece and let's move it to the left. Now remember, this conductor is going to stay in contact with this wire on these sides. But just the conductor by itself, moving through a region of magnetic field. So we'll set up a magnetic field region, and here is this metal bar. Now the metal bar has a bunch of electrons inside. It has a bunch of protons inside too. But for the metal bar, the electrons are mobile, or at least some number of them, some subset of the electrons are able to move freely. So what's going to happen is, if I move this bar through the magnetic field, the electrons inside are going to feel a force. Now the electrons are negative, and our vector diagram for forces on charges in magnetic fields tells us that as this bar moves through the magnetic field, the electrons get pushed to one side and the protons get pushed in the other direction. Now this happens with all objects. You've probably noticed this when you're walking through Earth's magnetic field, right? So here I am walking through Earth's magnetic field and all my electrons are being pulled this way and all my protons are being pulled that way. And yeah, it can be annoying sometimes when that happens. But and then if you run fast through Earth's magnetic field, if you increase the velocity, those forces are going to get even larger. Okay, so of course that's not a noticeable effect, but there really is happening. So anytime you've got charged particles moving through a magnetic field, there are going to be forces that tend to separate the charges just a little bit in most cases. Now if we make the magnetic field a little stronger and we move this conductor through at a high enough speed, we can generate a significant voltage. And that's it. At the end of the chapter, that's how we generate electricity. We move conductors through magnetic fields. And there are forces on the electrons inside there. And that sets up a voltage. Now I've written this as an EMF. Let's just see how much voltage or how much EMF we're going to have, we're going to be able to generate. Let's just throw some numbers in. Let's say that we're going to move the bar at 10 meters per second through this magnetic field region. Let's say that the magnetic field that we've set up is 2 Tesla. And let's say that the length of the bar is 20 centimeters. Now, the force acting on each one of these electrons is going to be given by Q times V times B And then there's a sign of theta here, but because the motion of the electrons is to the right, and the magnetic field is going into the board, I'm going to use a left-hand rule here because it's electrons. So I'm going to go rogue and use a left-hand rule. My thumb is in the direction of velocity, my fingers are in the direction of the magnetic field. That means that there's going to be a force on the electrons in the downward direction. Now, every step of the way here, so if this magnetic field went on and on and on and on and on, then these electrons, you know, I could follow a single electron and watch it as it gets pushed all the way across, or I can just say that there's an accumulated effect. No matter what distance we're pushing this through, the electrons don't have to go the whole distance through. The voltage will get set up immediately because of kind of this line of electrons that are inside here. So each electron is going to feel this much force. Now the energy that gets transferred to those electrons will be equal to the work. That takes us all the way back to what, chapter 7, where we introduced energy transfer. So we're actually going to be able to see and watch how much energy gets transferred into these electrons as they're getting pushed along that length. So the work would be the force, QVB, times the length. So now I've looked at the energy transfer. So the energy transfer that takes place all the way along here would be QVB divided by L. Now the electric potential, the voltage that gets set up, we can calculate that as the energy divided by the charge. So each charge is given this much energy along the length, and the potential then between here and here, that would be equal to the energy divided by Q. It says that the voltage that we get, the electric potential, is going to be given by V times B times L. That's it. There's our electric generator. We just have to move this conductor through and we'll set up this voltage. Now, similar to the voltage that's set up in a battery, the voltage is there waiting to be used, I guess. We don't really have a current set up until we provide a complete path where the electrons can make their way through all portions of the circuit. So if I pull this across, electrons are moving in all parts of the circuit. We've made a big deal of that throughout the course, that as soon as some of the electrons are getting pumped, all the other electrons get pushed along. I don't have to exert forces on all the electrons directly because they'll exert forces on each other. So the voltage is specifically coming from this part that's moving. That's where the voltage is. And then that drives current through the rest of the circuit, right? So kind of like a battery, right? What is happening mechanically by pulling this over to this side is replacing the chemical reactions that we saw going on inside batteries. Okay, so either approach will generate a current. It will push electrons through the circuit. So that's it. So V times B times L, that's what our formula is telling me for the voltage. So hey, I've got a 4-volt generator here. If I push this bar if I push this 20 centimeter bar at 10 meters per second through the 2 Tesla magnetic field. Now there's a problem with this, and the problem is I can't just keep pushing the bar at a constant velocity because that would require an enormous magnetic field, right? Here I am pushing the bar and I just keep pushing it and generating more electricity. But what we could do instead is we could oscillate the bar. What we could do is we could move the bar one way and then back, one way and then back. And so by doing that, by pushing the bar back and forth, we can continue to generate electric current. The current is going to oscillate directions. So have you guys ever heard of current that oscillates back and forth? Hey, it's going to be an AC generator, right? So that's what's going to happen here. We'll end up with an AC generator if I take this bar and have it move back and forth in this fashion. So, so that's what I've done down here. Down at the bottom I said, okay, here's an improvement on my generator so that we can continue to generate electricity. Let's have the velocity be a peak value of 10 meters per second, but let's have that oscillate like a sine function. So we'll just have the bar go out and back, out and back, out and back like this, and then the voltage that we get is going to be V naught times B times L times the sine of omega t. So we'll still get that very same voltage, but that's going to be our peak voltage. And then that peak voltage is going to get multiplied by a sine function. Done. So we've got an AC generator set up here. Okay, one more improvement. What we could do, instead of just pushing this out and back through this plane, what if we spin a rotating generator that will produce the same effect? And that's primarily how generators are designed. So generators are spinning loops of wire through magnetic field regions, and depending on how many loops there are, depending on how fast they're spinning, depending on how large the magnetic field is, depending on how large the loops are, specifically the lengths running perpendicular to the magnetic field, that's going to determine our EMF, or the voltage, for the generator. So, well, let's try and make a generator from this. So what we've got here then is, we want a VRMS of 120 volts. The frequency we're hoping for here is 60 hertz, and the frequency then, the frequency that we want in terms of radians per second is 377. So that's what we're after here, is an angular frequency of 377 radians. And what we're looking for then is, here is the voltage as a function of time. So I think it's everything here is kind of the same as what we did on the previous page. It's just a few more details. So what we're saying is that as a function of position, so let's say x equals 0 is right down the center of this generator, and the line here is going to get pushed back and forth like this, so that x varies like a sine function. So this takes us back to those chapters on oscillation. And then if that's the case with the displacement, then the voltages are going to be given by omega A times the cosine of omega t. And the V naught here is going to be given by omega times A. So let's see, we're looking for a 120 volt generator, 60 hertz. So it's the familiar electricity that we plug into with our outlets. And so the V naught that we're going to need here is going to be the omega times the amplitude. This is now an amplitude of oscillation, times the magnetic field times the length. And the peak voltage is going to have to be square root of 2 larger by a factor from the VRMS voltage. And so that's going to give us 170 volts. So let's say that the magnetic field is 2 Tesla and L is equal to 80 centimeters. Solving the equation that we have here and putting in 170 volts, it says that this thing would have to oscillate back and forth 28 centimeters plus or minus. So we would have to drive this bar back and forth a complete distance of 56 centimeters. So, and we have to do that 60 times a second. So that would be moving it out and back 60 times a second. And we go, well, let's go with the rotating generator that rotates 60 times a second. So what we could do is we could put these wires onto a rotating drum and then have them spin 60 times a second. That's probably going to be easier to design and operate mechanically. But again, there we go. That becomes our generator. So with the right number, and this is done with just one loop, So we're not using a huge number of loops for this. Well, let's see what the rest of the chapter has in it. It looks like we've already got our generator built and designed, and it's operating at the voltages we want. So one question that comes up with this is, with this generator that we've come up with, we're going to have to spin this generator, and that means we're going to need some mechanical energy coming in from somewhere. But can't we just get a generator that's frictionless? So if we can get a generator that can spin with no friction at all, will the generator operate freely forever? Can we just generate electricity forever without having to drive the generator with any mechanical type of energy? And let's see why that doesn't happen. So the bottom line here on this slide is no free lunch, and let's see what happens here. So let's go back to our simple example of, I'm going to take this bar and just move it at some constant velocity through the magnetic field region. Here are the forces acting, and what we came up with was we're going to have a voltage set up that's V times B times L. For the magnetic field going into the board and for our velocity going to the right, what we found was that the voltage is pushing the current. Now this is opposite to the direction of the electrons, but the current is going to be driven in this direction, and that makes this the positive terminal. So this becomes the positive terminal on our generator, and this is the negative terminal on the generator. And we can attach wires to that, and here is the light bulb. And the light bulb has a certain amount of resistance. And so the current that operates through our generator, through the circuit that we've set up, will be the voltage divided by whatever resistance we have. And the current then is going to be V times B times L divided by R. So that's how much current I will have operating through the circuit. So what we can see is, the speed of the bar going through determines the voltage, but the resistance in the circuit, whatever it is we're trying to light up or operate using this electrical energy, that resistance is going to help determine how much current there will be. And so, sure, there's a certain amount of voltage being provided by the generator. We got to divide that through by the resistance. Now, what happens when the bar starts to move? Current begins moving through that bar. So I'll write that as current. When the charges start moving through the current, there are going to be additional magnetic forces. At first, the magnetic forces were pushing the current in this direction. But now that the current's moving, and there's an external magnetic field still, that's going to create a force in this direction. So once the current starts moving this way, I'm going to have a force, and notice the direction of that force. That force is opposing the motion of the generator. So that says if there is a current running in the circuit, then I'm going to have to continue pushing the bar. I can't just push the bar once and it will go forever and assume that just because there's no friction, because there will be magnetic forces slowing that bar down. And we can find out how large these resistive forces are. These resistive forces are going to be I times L times B. That's an equation we've been using, well, since chapter 27. So that means that the mechanical power, the force that we would need to push with to maintain constant velocity would be a force that matches this. So I would have to bring in something that pushes my generator along, something that forcefully spins my generator. And that mechanical force would need to match I times L times B. So the power in that mechanical force that's turning my generator needs to be I times L times B times V. And that's going to be the same thing as V times B times L times I, Well, that's the same thing as voltage times current, and that's going to be the electrical power. So what we've shown here is if we build the perfect generator where there's no friction as it spins, we're still going to have to put in some sort of mechanical energy to spin that generator. And for every joule of electricity, of electrical energy, every joule of electrical energy that we produce, we're going to have to put in 1 joule of mechanical energy to keep the generator moving. Okay, so no free lunch. Energy is conserved. And so what that says is, if I'm going to get out 1,000 joules of electrical energy, I'm going to have to put in 1,000 joules of mechanical energy. I'm going to have to find some way of spinning that generator. Okay. All right, so let's, I think I put some more numbers in. And so I put, I think I changed them. So the velocity, let's push the generator bar at 20 meters per second. Let's say the length is 40 centimeters and the magnetic field is 1.5 Tesla. Multiplying those numbers together gives us 12 volts. So this is a 12 volt generator. Now let's say that we take our 12 volt generator, we operate it, and it's lighting up a resistor, a light bulb, that has a resistance of 4 ohms. Well, that says that my 12 volt generator running current through a 4 ohm light bulb is going to maintain 3 amps. The power then, that the electrical power we have going into that light bulb is V times I. That's 12 volts times 3 amps. That is being powered at 36 watts. 36 joules per second of electrical energy is going in to light up that light bulb. Now, if I'm going to get 36 joules of electrical energy, of light coming out of my light bulb, then what that says is I'm going to have to put in mechanical energy at that very same rate. If I'm getting out 36 joules per second going into lighting the bulb, I'm going to have to come up with 36 joules per second of mechanical energy. Now what we had said was that the force we're going to need to push with is going to be equal to I times L times B, because that is the opposing magnetic force. So I've got to push with enough force to offset this opposing force, and putting those numbers together, I end up with a force of 1.8 Newton. That's not very big, but I have to push this at 20 meters per second. Ooh, that's pretty fast. Yeah, why did I pick 20 meters per second? So 1.8 newtons, 20 meters per second, that's 36 watts. Okay, so I can just, we ran the formulas before, and now we're just putting numbers in and looking at the numbers kind of side by side. In terms of electricity, we're calculating voltages, currents, and power. In terms of mechanical energy, we're asking how much force do I have to push with, what's the speed at which that bar needs to move, and how much power will that require. Okay, and the numbers match up. All right, this is just kind of the same picture. Now what we refer to this as being an induced current. Now consider this, compare this with a battery. With a battery, we've got a chemical reaction that's kind of built into the circuit itself. And so there's a chemical reaction and the wires are hooked right up to that chemical reaction. The chemical reaction generates a voltage. It also generates an electric field. So the battery is actually generating an electric field that pushes the electrons along. Let's think about this. If I want to get a bunch of electrons moving, what forces could we use? And we only really have 2 choices. We can either use an electric force or we can use a magnetic force. Those are the forces available to push on charged particles. In a battery, we're generating an electric field that sets up through the circuit and pushes the electrons through. So the fields that are set up are right inside the circuit itself. But with induced current or induction, those fields that we're using are being set up externally. So what we're doing is we're taking an external magnetic field, we're moving a bunch of charges through it, and a current shows up. We go, oh, it's a miracle. Look, a current has been induced. We didn't directly connect anything to those wires. We just ran them through this region where there's a field. Well, what those charges are connected to, those charges are experiencing a force due to the activity of the charges that are maintaining the magnetic field. So that magnetic field is being maintained by other charges that are in motion, and those other charges are creating a magnetic force that pushes this charge along. So in the examples we've been looking at, it's a magnetic force that we're using. So we can use magnetic forces or electric forces to induce current. We're going to see examples of both. And that's basically the same picture that we had before, except they've flipped the magnetic field the opposite direction. Okay, now the title of the chapter was electromagnetic induction. That's creating the currents in this inductive manner. And then it was also called Faraday's law. So if you think back to Gauss's law, Ampere's law, they were kind of these high-level theorems that told us how fields are related to charge distributions. But what Faraday's law tells us is that if we keep track of the rate at which magnetic fields are varying, specifically something we're going to call magnetic flux, that will allow us to go and determine how much EMF is going to show up in a generator, for example. Now, this is kind of a high-level theorem. We talked about what forces can move charges. We can either use magnetic forces to induce currents, or we can use electric forces to keep currents moving. And Faraday's law takes both into account, and we'll see how. This is kind of interesting. So let's see what all this math means. What do these formulas mean? This formula right here, we say that there's a region where there's a magnetic field. Now, we just looked at that, where we were using magnetic fields to generate an electric current. If we look specifically at the region where that magnetic field is located, and we multiply by the area. Now, I know this is an integration, but basically what they're doing is they're taking the magnetic field, multiplied by the area, and we call that magnetic flux. Now, if you think back to Gauss's law took electric fields and multiplied by area, and we called that electric flux. So this is magnetic flux, and 1 unit of magnetic flux is called 1 Weber. 1 Weber is 1 Tesla times meter squared, and I will never use that unit. We have too many units, that's it, I've had it. We're not introducing any more units, no Webers. Just say Tesla meters squared, right? We don't have to have a special unit for everything. Okay, same picture that we drew. What they're saying now is the magnetic flux. Now, the magnetic flux, we said, could be thought of as the magnetic field times the area. Now, Faraday's law says that if we take the magnetic flux and find out how it's varying in time, so it's not just the value of the flux that tells us how much EMF will generate, it's how rapidly is that flux varying. So this is kind of remarkable that Faraday's law can actually measure a certain amount of flux, see how it's changing, and that actually is going to be related to how much EMF is generated. So let's try that. Let's take our example where we pulled the bar over to the right. What's happening with the flux is, as I pull the bar over, I'm picking up additional flux. Every time this bar moves by a distance of dx, the area increases by L, that's the length of the bar, times dx. And that's going to increase the area. So the d area is the amount that the area increases during the time dt. So during a short interval of time, if that bar is moving, it will travel a distance dx. That's going to increase the area. And so here's what our formula, here's what Faraday's law looks like. The EMF depends on the rate at which the flux is changing. The flux is given by the magnetic field times that, or the increase in the flux is that magnetic field times that little section of area that we added on, and that's happening during time dt. The area is increasing by L times V times dt. The dt's cancel, and it says the EMF that we did is BLV. Now, the textbook leads with this approach and says, look, we can use Faraday's law to calculate the EMF. And I think this one's complicated. I want to go back to our example where we just directly looked at the bar moving through the magnetic field and used our magnetic force formula. Okay? So I think there are many cases with these generators where it's much easier just to use that direct magnetic force formula to determine how much EMF, rather than going the route of Faraday's law. Okay. So anyway, either approach will work. I'm gonna suggest that Faraday's law can be more complicated. Let's do a flux calculation real quick. So let's say that we have a region where we have a wire surrounding a magnetic field region, and we want to find out how much flux there is. So the question is, I've got a magnetic field, but the magnetic field is only passing through this area. So when I calculate flux, should I take the magnetic field times the entire area of the circuit, or should I just take the magnetic field going through this area? And the answer is, as you might guess, I just want to use this area where the magnetic field actually is. That's the flux. Sure, I've got this big area defined by this wire loop, but when I carry out the integration, the magnetic field here is 0. So I'm not going to include flux from this region, so only where the magnetic field is present is where we would calculate the flux. Okay, and then if we tip things at different angles, so the flux can vary depending on the direction of the magnetic field relative to the area where we have that circuit loop taking place. So if we take our circuit loop and tip it, we can change the flux. And the flux will vary like the cosine of theta. So when theta is equal to 0, that says that the area vector lines right up with the magnetic field vector, and that's where we have the full area of the, or the most direct magnetic field passing through the area is if we tip it, so that the surface area itself has magnetic field lines running perpendicularly through that area. And so if you remember, the area vector is defined not as within the plane of that surface, but perpendicular. Area vectors are defined to be perpendicular. That's a unique way to determine the orientation of that area. And so, when the angle goes to 0, that's the most flux. When the angle goes to 90 degrees, we're not picking up any flux at all. So here's 3 possible orientations. Let's say we have a loop of wire, or in this case, we have several loops. The area vector, so there's a plane here where those wires, I got 3 circles of wire, and we're looking from the side. And so the area vector is pointing perpendicular to that. Now, if you're thinking, well, wait a minute, is the area vector here or here? That's the right question. So it does turn out with these definitions that it's kind of a coin toss. I can either define the area this way, or I can define the area this way. Now, the way that we end up often defining the area is we look to see what direction the current will be moving, and we use a right-hand rule. If we put our fingers of a right hand along the direction of current, the area vector, the thumb will be in the area vector direction. okay, is usually the simplest way to define that. So here's the magnetic field. Here's an example where the coils are oriented at 90 degrees and there's no flux. Here, we've rotated the coils so that the angle now between the magnetic field and the area vector is 45. So that's going to give us BA cosine 45. And then finally, we've rotated it until the area vector lines right up with the magnetic field direction. And there the angle is 0, and that's where we're going to get the maximum flux. Okay. Now you can see that there's also definitions of positive and negative flux here. But that just depends on how we've defined the area vector. Remember, we could have started here, and then as it rotated, we come to here, and then here we would be tipped at 180. So there's just some sign flips that you have to watch for in the formulas. And in most cases, I don't think it's, for us, I don't think that's even going to show up. So let's look at another example here. We have a square loop. I always feel like loops should be round, but this loop is square. So there's a loop of wire. Each side of that is 5 centimeters. It's in a magnetic field. The magnetic field is 0.16 Tesla. How much magnetic flux do we have? What is the magnetic? Wait, that's before. Oh, what is the magnetic flux under the conditions of the magnetic field is perpendicular to the face of the loop. Magnetic field is at an angle of 30 degrees to the area vector. Okay, and then what is the magnitude of the current in the loop if it has a resistance of, that's not much resistance, and it's rotated from position B to position, okay. So a lot of stuff to read through here. Let's see how this Faraday's law approach works. So what we would say is, first of all, from my reading, it looked like this was picture the starting location. So the flux starts here. The flux starts out as B times A, and the angle here is 0, cosine of 0 is 1. I'm getting the full flux, the maximum amount. But here we've tipped at 30 degrees. So if I take one loop, a square loop, right there, and rotate it by 30 degrees in the magnetic field, what that's telling me is the flux is changing. And so how are we going to calculate flux here? Well, the flux is going to be the magnetic field integrated over the area vector. Since the magnetic field is uniform here, the flux can just be written as B times A times the cosine of theta. All right, so the magnetic field is uniform. Now the EMF formula from Faraday's law says that we want to take this flux and take a derivative with respect to time. Well, the magnetic field's not changing, the area's not changing, oh, it's the angle. So in Faraday's law, it could be the magnetic field that's varying, it could be the area that's changing, or it could be the angular orientation that's changing. I have to watch for time dependence in any of those locations. It turns out in this case, theta is varying, and what we can say is that theta is equal to, let's say it's equal to omega t. So what's happening is this is spinning at some rate, at some constant speed. So what we'll do then is take the time derivative of this expression. The time derivative is omega times the magnetic field times the area of the loop is square, times the sine of omega t. And this stuff right here, omega b times a, that's going to be the peak EMF. So now, what did they say about the frequency? I think I may have changed the frequency information. Yeah, they say that we've moved in 0.14 seconds. I just went ahead and did this in terms of a certain speed at which we're going to be rotating. So instead, I went with, I said that let's just say that this thing is going to be spinning 10 times a second. And so that would give us 63 radians per second. And putting all the numbers in, that's going to give us a peak EMF of 25.1 millivolts. So that's what we've got here. Now, as far as the orientation of the area vector, we can take a quick look at that. So the way that the vector, the area vector, is defined, let's say that I have this square loop, and if I decide to say the area vector is into the board, what that does is, using my right hand, it tells me the direction of positive current or positive voltage, or positive direction in general. So mathematically, if we define the area vector in the direction of my thumb, then my right hand, the fingers will go in the direction of positive motion around the perimeter. My left hand will show me what direction is negative. And so with this definition, if I choose to put the area vector into the page, then positive direction around the perimeter would be this, would be clockwise, and negative direction would be back like this. And so that's what I've shown here. Now we also could have defined the area vector the other way. If I had chosen to have the area vector come out of the board, then positive direction would still be given by my right hand. My thumb points out of the board, and so my fingers are pointing in this direction, and then negative directions would be opposite. Now, if you think about that, you go, well, wait a minute, how can it be reversed? Because picking the area out of the board, let's say we do that first, but then we flip the area over, and now the area is going into the board. And so from our view, it looks as if the direction of motion has changed, when in reality, the direction of motion has stayed the same. We just flipped the object. Okay, so that's just mathematically what's going on behind here. And again, I don't know that we're going to need to ever have to deal with that. So here's an example using Faraday's law. It says, let's take a bunch of loops of wire like this. Now there's the magnetic field. What would happen if I take a bunch of loops of wire, I place them in a magnetic field, and then I stretch them out like this? And you go, well, the area decreased. The magnetic field stayed constant, but the area decreased. And that would say that the flux through the coils of wire has decreased because the area has gone down. Now what you guys might also notice in these examples is what's happening here is when I change the area, these wires are going through the magnetic field and setting up a magnetic force on the charges. If I have a velocity in that direction and I have a magnetic field here, there's going to be a force in this region, in this direction, while down here the velocity is upwards, the field. So I'm going to get forces here and here, magnetic forces, and that's what's causing the EMF. That's what's causing the induced current. So you can see what's going on here is Faraday's law allows us to go in and do these calculations based on flux. But Faraday's law isn't telling us exactly how the EMF got set up. Faraday's law works, but it doesn't tell us the details of where the forces are actually being applied that are setting up the current. It's analyzing what's going on with the wires in this situation. We can go, oh, when these wires move through the magnetic field in these directions, they experience magnetic forces which will drive the current. Okay, now the book uses something called Lenz's law to keep track of direction of current, and that's fine. You can take a look at Lenz's law and see what you think. To me, Lenz's law is another one of those mysterious rules that we can follow and we can determine what the current, but it doesn't give us the details. I really like the approaches where you can say, here are the forces acting on the charges that are actually pushing them through the circuit. Okay, now there's a minus sign in Faraday's law, and the minus sign is there to help give us direction. Okay, and this is a statement of Lenz's law. Lenz's law says that the current that ends up being produced by an induced EMF, the current will be moving in a direction that tends to oppose the existing magnetic field. Okay. All right. So that's the direction it will be in, and that, it works. Lenz's law definitely works. Okay, so if we're going to be using Faraday's law, what we want to be able to do is do measurements of how much flux do we have, and be able to keep track of how the flux is changing in time. So it's all the steps that we've gone through in the examples that we have been looking at. Okay, here is some practice. Now they're going to say it's practice with Lenz's law. I want to practice just by looking at the motion of the current. So if we have a current loop, and there's a magnetic field region here, as we pull the loop out from the magnetic field region, the flux will drop off. So that says that I'm going to define the area vector to be in the same direction as the magnetic field vector. That's usually the easier definition. So I'm going to pick the area vector to be coming out of the board here in the same direction as the magnetic field direction. And so what will happen then is, with that definition, the flux is positive, but as I pull this out, the flux is positive, but it's dropping. Now, if the flux is dropping, then its derivative is negative, and since there's a minus sign in Faraday's law, a negative flux variation creates an EMF in the positive direction. So that says that I can put my thumb in the direction of the area vector, my right hand, and the fingers on my right hand will say that that's the direction of the EMF. Now that's using Faraday's law. Faraday's law didn't tell us exactly where the forces are coming from. I'm going to say when we pull this loop out of that field, the force is coming from right here, because that's the section of the loop that's moving through the magnetic field in an orientation where the velocity is here, the magnetic field is coming out of the board, so I can do velocity, magnetic field, and that tells me that the force, the magnetic force, pushing on positive charges through that region would be downwards. So Faraday's law just says I look at the whole thing and see how the flux is varying and determine what the overall EMF will be. But the direct approach says I can point right to the locations where the force is being applied. There is no force over here. That section is no longer in the magnetic field. There won't be any magnetic forces creating an EMF over here, but there will be here. Now these sections are going to have forces, let's see, velocity is here, magnetic field is here. So again, this is going to be forces that are down. So I'm going to get forces here that are down. I'm going to get forces here that are down. But the downward forces on those sections of wire are not lined up with the wire itself. In order to push charges through the wires, I have to get magnetic forces that are in the direction the wires are oriented. So this downward force that's being produced doesn't have an effect here, doesn't have an effect here in terms of EMF, but it does have an effect here. It's over in this region where that force is lined up with the wiring itself, and the charges will get pushed. So they're being pushed from here. Most forcefully right from here, not quite as much here, here, and here, and then it drops down to zero. And the reason we're getting a net EMF is because this portion has exited the magnetic field, and so there's not going to be any forces on those charges anymore. So this one is not being offset by an opposing force, and these forces are able to generate the current. Same thing here. What we've got is the Faraday's law approach says that the flux is decreasing, and if the flux is decreasing with respect to time, that's a negative derivative on the flux, and so the EMF will be in the positive direction. Now what's changed here is that the magnetic field is going into the page, and so I'm going to define the area vector to also be into the page, and so a right-hand curve says that the EMF will get set up here. Now this one too, we can go in through and show what's really happening. Faraday's law gives us the correct value for the EMF, but it doesn't tell us where the EMF is being generated or whether it's a magnetic or an electric force that's doing the work. A direct approach says as the wire moves through that magnetic field, if I have a velocity in that direction, and the magnetic field is here, there's going to be a force on positive charges set up all the way around. So in this case, the contraction, the motion through the magnetic field is symmetric. So whereas in this case, the magnetic force was coming from right here, here we're going to get magnetic force all the way around. Okay. And so forth. So we can move through each of these examples and kind of reason our way through in terms of magnetic flux. Okay, let me. Yeah, here we go. And so here's an example of how this would be carried out. Let's say that the flux is given by B times A times the cosine of theta. Let's say that we have a region, this is my own made up example. Let's say we have a region where the magnetic field is increasing. So it's not, the area here is not changing. I think this is one of the examples. Yeah, this is it. This is kind of example C, where we have some loops moving in the region where there's an existing magnetic field, and we're moving into a region where the magnetic field is getting stronger. So there's been a bar magnet set up. We're taking a loop and we're moving that loop over the bar magnet. Now as we get closer, the magnetic field is getting larger. So I'm going to do a B versus T graph. If I define the area vector to be in the same direction as the magnetic field vector, then what I can say is that the flux is also increasing. So as the magnetic field increases, the area is staying the same, but the flux will increase. Remember, the flux can increase or decrease either because the magnetic field is varying, the area is varying, or the angle between the two is varying. So the phi dt is positive. I can see that's a positive slope. So E will be in the negative direction. Now I defined the area vector to be into the board, and so my right hand shows me the direction of positive motion, and my left hand shows me the direction of negative motion. Since the EMF is positive, the EMF will be moving in this direction, and that's the direction that the current will be induced. The EMF is going to be driving that. Okay, let's see, I'm trying to decide when we want to take our break here. Yeah, this is probably a good time, so let's go ahead. Let's go ahead and take a break for 10 minutes or so, and then we'll pick up again with chapter 29.